All right, lesson 6.6. We're going to the hospital. That is L'Hopital's rule. That's a French mathematician. What matters is it's used to evaluate limits. And so if a limit is indeterminate, and that would be 0 over 0 or infinity over infinity, plus or minus, we can then take the derivative of the numerator and denominator and then reevaluate. If it's still indeterminate, we can apply it over and over again until we have an answer. So, if I look at number 1, the limit as x approaches infinity. If I plug in infinity, the numerator is going to infinity and the denominator is going to infinity. That's indeterminate. Now, when I am asked to go the limit as x approaches infinity, that's the right-hand behavior. And if I see the denominator is more powerful than the numerator. So as I put in 100, 1,000, 1 billion, the denominator is clearly increasing faster than the numerator. That answer is 0. If it's the other way, again, this works for the right-hand behavior. If the numerator is going to infinity faster than the denominator, this one's going to infinity. Or you can say this doesn't exist. For number 3, if I plug in 0, I have 0 over, be careful, e to the 0 is equal to 1. So this is just 0 divided by 1, which is equal to 0, not indeterminate. So be careful to assume it's going to be indeterminate. For number 4, if I plug in 0 and plug in 0, here, e to the 0, that's 1 over 0. That is not indeterminate. That's undefined, doesn't exist. But what happens from the left? How would we do that? And so from the left, as I plug in negative numbers here, like negative 1 to negative 0.5 to negative 0.2, what's happening here? What direction is it going from the left? And the answer is this is going to negative infinity. There is an asymptote at 0. To the left, it goes down forever, and to the right, it goes up forever. All right, number 5. Plug in 0 here, and you don't assume it, but e to the 0 is 1. So 3 take away 3 is 0 over 0. So this is indeterminate. That's what that means. That's not a percent sign. So L'Hopital's rule says you can take the derivative and then reevaluate. So the derivative of 3 is 0. The derivative of this, you copy it, negative 3 e to the 3x, and it has a hook of 3. And then the denominator, the derivative of x is 1. And now we reevaluate. That means plug in 0 again. So e to the 0 is 1. Negative 3 times 3, that's negative 9 divided by 1. And so this limit, the answer is negative 9. For number 6, if you plug in negative or positive infinity, notice that this is going to infinity. This is in the form infinity times 0. So the left-hand behavior of e to the x is 0. The left-hand behavior of x squared is infinity. So infinity times 0. I'm going to change the way this looks so it's in a form where I can do L'Hopital's rule. It needs to be a quotient. So for a quotient, I'm going to change this to x squared and then e to the negative x. So e to the positive x, put it in the denominator, it's e to the negative x. They're equivalent. Now, when I look at it, the left-hand behavior here, again, is infinity. And then the bottom, as I go, a negative times a negative actually makes it positive infinity. Both are going to infinity. So this is in the form infinity over infinity. Now I can apply L'Hopital's rule to this. So the derivative, and make sure you keep the limit notation until you can actually evaluate. So the derivative of x squared is 2x. This is copy it. And then the hook. Again, it's still indeterminate. In fact, it's now negative infinity over negative infinity. So one more time. And then don't forget the limit notation. So that's 2. Now we're going to be able to evaluate. And we're going to copy negative e to the negative x. And then the hook. So a negative times a negative is positive, and a negative times a negative is positive. So this, the denominator, is going to infinity. This is now 2 over infinity, And another way to think of it is it's going to 0. So when the denominator is going to infinity and the numerator is a constant, that's it. It's going to 0. So it's like 2 over a billion, 2 over a trillion, 2 over infinity. It's getting closer and closer to 0. And number 7, when we have two fractions, we're going to write that as one fraction. So we're going to get common denominators. That's going to be ln x, x minus 1. So we're going to multiply the first times x minus 1, top and bottom. And then multiply the second one by ln x, top and bottom. And now we have common denominators. And now we have one fraction. So if I plug in positive 1, 1 take away 1 is 0, and ln 1 is 0. Ln 1 is 0. So this is 0 over 0, which is indeterminate. And we actually don't want to write 0 divided by 0. We just want it in our head. Okay. Next, what do we do once it's indeterminate? Make sure you keep the limit notation. We're going to take the derivative. So the derivative of x, the derivative of negative 1 is 0. The derivative of ln x is 1 over x. The denominator is going to be the product rule. The first times the derivative of the second plus the second times the derivative of the first. I'm going to multiply top and bottom by x to kind of clean it up a bit. So if I multiply by x, so multiply top and bottom times x, I get 1 times x. 1 over x times x is 1. And then if I multiply this, I get ln x times x. And then x times 1 over x just simplifies to 1. That gives you x minus 1. And then again, if I look at it carefully, plug in 1, I get 0. If I plug in 1, I get 0. 1 take away 1 is 0. This is still indeterminate. So, one more time, we're going to take the derivative. And then you have to keep writing the limit notation. So the derivative of x is 1. So as soon as I know the numerator is a constant, this is it. So there's nothing more I can do other than evaluate, or it doesn't exist. This is going to be the product rule. That's the first times the derivative of the second plus the second times the derivative of the first, which is 1. The derivative of x is 1, and then the derivative of negative 1 is 0. At this point, I can simplify it. Now, x times 1 over x is just 1. So when I plug in, I have 1 on top. Ln 1 is 0, but I still have 1 plus 1 that's left. So that limit is 1/2 after we evaluate it at 1. That's L'Hopital's rule. Is it indeterminate? Then you take the derivative of the numerator and denominator. Again, you might have to do algebra, so it's in a quotient, so you can see it again. And then once it's in the form of a quotient, again, is it indeterminate? Again. And sometimes you stop when the numerator is a constant, though you're constantly evaluating to see if it's still indeterminate. Once it's not indeterminate, then either it doesn't exist or there's an actual number. What happens here for this limit? Well, first, I'm going to factor. If I plug in negative 1, I do get 0 over 0. So I can definitely, without using LR, I'm not sure what LR is. Anyways, here's another way to do it. We can factor this. And so if you factor out a 2, that's x squared take away 1. And then x squared subtract 1 is a difference of squares. And then you can remove the discontinuity and then plug in negative 1. And negative 1 subtract 1, negative 2 times 2, that's negative 4. Number 9, here, if I had used L'Hopital's rule, so this is by, I think, without L'Hopital's rule. I think that's what LR, right? Now okay. Here, with L'Hopital's rule, it is indeterminate. I can take the derivative of the numerator, and I can take the derivative of the denominator, and then plug in negative 1, and I get the same answer. Genius I am. All right. Number 10, LR. I don't know what it is thinking. All right. The following limits are not 0 over 0 or infinity over infinity. Identify the form and tell which are indeterminate. So if I plug in infinity here, 1 over infinity is going to 0. And 1 plus 0 1 plus 0 is 1. So this is 1 to infinity. That is indeterminate. Here, I have 0 to the 0. That again is indeterminate. Here, if I plug in infinity, it's infinity to 0. That's indeterminate. I don't know what that means. Indeterminate means I don't have a way to evaluate that. And then 13, if I plug in 0, sine 0 is 0. So it's 0. 1 over 0 is undefined. Now, on the right side, this is still going to 0. Here, 1 over x is a reciprocal function. If you think of the behavior at 0, it's going to negative infinity, or positive. So it's going to positive infinity on the right. Now 0 to infinity does have an answer. 0 to anything is going to equal 0. So this one is not indeterminate. All right, a few more left. Find the following limits. So if I look here, I want to write this in a way where I can evaluate it. So the way it looks right now, with the variable in the exponent, I can't put in L'Hopital's rule the way it looks. Now I'm going to tell you, this right here is the calculus definition of what the number e is equal to. So in math, we know e is a number. Where does it come from? Right here. It's this limit is what e is equal to. And that's where it comes. So we're going to have a calculus understanding of this when we get there. So I already know what the answer is. It's e. And I'm going to show you why the answer is e. As it's blurry. Now it's not blurry. All right, so step number 1, we're going to write down y equals this limit. We're going to create an equation. Because we're solving an exponential, we're going to write it as a logarithm. And we're going to use ln for our logarithm. Now, because of that, we can then do some logarithmic properties. So that exponent x now can go in front. The limit is always going to be the very first thing you're going to write down. Now, the right side I'm going to write as a quotient. So this is something new to think about. So to write it as a quotient, I have ln 1 plus 1 over x, and then I'm going to say x to the negative 1 in the denominator. Now, if I plug in infinity, we need to understand 1 over infinity means 0. What does 1 over infinity mean? 0. So 1 plus 0, that's just ln 1. That means the numerator is 0. If I look here, x to the negative 1 is really 1 over x. And again, if I plug in infinity, 1 over infinity again is 0. So in other words, this is 0 over 0. It's now in a form where then we can apply L'Hopital's rule. So on the right side, we're going to take the derivative. So the derivative here is what you see. And then the derivative of that. Now, the derivative of 1 is 0. The derivative of 1 over x, think of that as x to the negative 1. So it's negative x to the negative 2 as the derivative. And then the bottom is going to be negative 1x to the negative 2. Same thing. Now we're going to do some algebra to simplify this. Whenever you divide fractions, you multiply times the reciprocal. So I have negative x to the negative 2 over 1 plus 1 over x times the reciprocal of what I just have there. And if you notice really carefully, negative x to the negative 2, they simplify out. And what I'm left with is 1 over 1 plus 1 over x. At this step, you can actually understand and plug in infinity. If I plug in infinity, what is 1 over infinity? It's 0. So all I'm left with then, if this is 0, is 1 divided by 1, which equals 1. We can now evaluate that limit. So I have ln y is equal to 1 once I plug in infinity. Now I'm going to write it exponentially. So we have a logarithm. So inside the logarithm's y, what base does ln have? And then what's the exponent on e? And I don't need the 1. So the answer is e. And I knew that at the beginning. There's the answer. All right, last one. I know it's a little algebra heavy today, so we're going to have to work hard to get our algebra skills up to calculus. Here we go. Blurry. Let's see if I can make it not blurry. Not blurry. So, again, this is indeterminate, but we have a variable in the exponent. So we're going to approach it the same way when we have a variable in the exponent. So I'm going to create an equation, and then I'm going to do a logarithm to both sides. So I'm going to go ln y is equal to ln, again the limit will always go first, ln x to the exponent 1 over x. At this step, the 1 over x can be written in front of the logarithm. That's the power rule. And then as you can see, you could write this as a quotient, so I could do L'Hopital's rule. So I'm going to write down the limit as x approaches infinity, and this is 1 times ln x over x. This is going to be infinity over infinity. So a logarithm right-hand behavior is infinity, just goes there slowly. Because the numerator is going faster, so at this point I can actually evaluate this limit. The numerator is going slower than the denominator. So as I go put in 100, 200, 1,000, a billion, a trillion, the denominator is increasing at a faster rate than this. So this is going to 0. If I did L'Hopital's rule, you could also see it that way. The derivative of ln x, the derivative of x, and again, what's 1 over infinity? What does that equal? And we're learning that equals 0. Then I write this exponentially, so y equals e to the exponent 0. So that means the answer to this limit is 1. All right, there's your lesson on L'Hopital's rule. You went to the hospital with me. Hopefully you're doing okay. And then we'll do our assignment together. Mr. G Math, over now.